Good morning to all. I am A.R.AKINI, Assistant Professor of Chemistry, A.D.M. College for Women, Autonomous, Nagapattinam. Now I am going to present my topic on stereochemistry. This topic present in second BSc Chemistry. Okay, first of all going to the presentation overview. Stereochemistry, isomerism, structural isomerism, stereoisomerism, configurational isomerism, conformational isomerism, optical activity and then chirality. Next one, first of all, what is the stereochemistry? Stereochemistry, a subdiscipline of chemistry, involves the study of the relative spatial arrangement of atoms that form the structure of molecules and their manipulation. The study of stereochemistry focuses on stereoisomers, which by definition have the same molecular formula and sequence of bonded atoms. It is a constitution, but it differs in the three-dimensional orientation of their atoms in space. For this reason, it is also known as 3D chemistry. 3D means three-dimensional. The prefix of stereo means three-dimensional. An important branch of stereochemistry is the study of chiral molecule. Stereochemistry, the entire spectrum of organic, inorganic, biological, physical and especially supramolecular chemistry. Stereochemistry includes method for determining describing the relationships, the effect on the physical or biological properties. This relationship impart the molecules in question and the manner in which these relationships influence the reactivity of the molecules in question. It is a dynamic stereochemistry. The stereochemistry is the chemistry of compounds in three dimensions. The term has been derived from the Greek word. It is a stereos, meaning solid. Stereochemistry is an important branch of chemistry and is concerned not only with the geometry of the molecules, but it is also helpful in the understanding the pathway of chemical reaction. Next one, what is the isomerism? The isomerism, the phenomenon of two or more compounds having the same molecular formula but different physical and chemical properties is known as isomerism, and these compounds are individually referred as isomers. Next one, why are isomers important? One isomer can have a single bond while another isomer has double or triple bonding, which means that the isomer is unsaturated and is open to bonding with other molecules, while the single bonded one is saturated and not open to bonding. The following chart shows different types of isomerism. Next one of the classified the isomerism. The isomerism classified have two types. One is a structural isomer. Next one, stereoisomerism. Structural isomerism have classified four types. First one, chain isomerism. Second one, positional isomerism. Third one, functional group isomerism. Fourth one, metamerism. The next one, the stereoisomerism have classified into the two types. First of all, one is a geometrical isomerism. Second one, optical isomerism. Next one, what is the structural isomerism? The structural isomerism is here. The compound having structural differences are classified as structural isomer. This type of isomerism is due to structural differences. Some common type of structural isomerism are chain, position, functional group isomerism, metamerism and then tautomerism. The structural isomers are those isomer is which the atoms are completely arranged in a different order with the same molecular formulas, and these are the molecules having the some same kind of molecular formula with different connectivities depending upon the order they are put together. And the structure of alkane C4H10 is one of the simple examples representing a structural isomer with different isomers with the increases in the number of carbon atoms in the alkane molecules. The structural isomer is increases, and the isomer differing in the atomic arrangement of the molecules without any kind of references to the spatial arrangement are known as the structural isomers. The phenomenon of these structural isomers is called as structural isomerism, and the structural isomerism is also called as a constitutional isomerism as per IUPAC. IUPAC means in International Union Pure and Applied Chemistry. It is a kind of isomerism where the molecules having the same molecular formula with different orders and bondings as opposite to that of the stereoisomerism. Next one, chain isomerism. When two or more compounds having same molecular formula but a different carbon, they are referred to as chain isomers, and the phenomenon is termed as chain isomerism. For example of N-pentane, isopentane and neopentane are the same molecular formula, but the arrangement of the 5 types of carbon attached to the group, but the arrangement of chain very different. Next one, positional isomers. In position are constitutional isomers that have the same carbon and the same functional groups but differ from each other in the location of the functional groups on or in the carbon chain. For example of first one is a propyl bromide, and then second one is a isopropyl bromide. It is a example of the constitutional isomerism. Next one, functional group isomerism. Two or more compounds having the same molecular formula but different functional groups are called functional isomerism, and the phenomenon is termed as functional group isomerism. For example, the molecular formula of C3H6O, it is a represent an aldehyde and a ketone. It is a example of acetone and propanol. It is a two type of same molecular formula, but the arrangement of the functional group is very different. Ketone C double bond O, and then aldehyde is CHO. And next one, metamerism. This is also one of the structural isomerism. Metamerism is a special type of isomerism. In this case, the isomer known as metamers have the same functional group. The metamers are members of the same class. For example, C4H10O can be represented as the metamers are the isomers having the same molecular formula but different alkyl groups on two sides of functional groups. This phenomenon or isomerism is called metamerism. Next one, the structural formula of diethyl ether and methyl propyl ether are CH3, CH2O, CH2, CH3 and CH3O, CH2, CH2, CH3 respectively. Both have the same molecular formula of CH4H10O. Next one, it is a classified the stereoisomerism of the stereoisomerism classified of the two types. One is a configurational isomerism, another one is the conformational isomerism. The configurational isomerism are classified the two types. One is a geometrical isomerism, another one is a optical isomerism. Geometrical isomerism is classified the two different types. One is a cis, another one is a trans. The optical isomerism have classified as two types. One is a diaceamers and then another is a enantiomers. The diaceamers have two different types. One is a trio and another one erythrio types. Next one, the enantiomers have two different types. One is a R isomer, another one is a S isomers. First of all, what is the stereoisomerism? It is a due to difference in arrangement of atoms or groups in space. It is a two types. One is a conformational isomerism, another one is a configurational isomerism. Next one, first it is a configurational isomerism is a two molecules with the same constitution but a different configuration. For example, of some IUPAC name for the constitution, different IUPAC prefix for configuration. And the configurational isomer cannot be interconverted without breaking bond. And then the configurational isomer is the two types. One is a geometrical, another one is a optical isomerism. First one is a, what is the geometrical isomerism? The geometrical isomers are two or more coordination compounds with contain the same number and the types of atoms and bonds. For example, the connectivity between atoms is the same, but which the different spatial arrangement of the atoms. Next one is here, it is example of this isomer in which like ligands are adjacent to one another is called cis isomer. The isomer in which like ligands are opposite on one another is called trans isomer. For best example of a cis butene and then trans butene. It is here for the hydrogen group is the same side, it is called cis isomer, and then same functional group is the opposite side, the functional group is called trans isomerism. It is here best example of trans butene. Next one is optical isomerism. Optical isomerism arises to the differences in rotation of plane polarized light. So far we have discussed conformational and geometrical isomerism, in which isomerism have different physical and in few cases chemical properties, but optical isomer have similar chemical and physical properties differing only in rotation of plane polarized light. It is here a compound that rotates the plane polarized light is known as the optically active compound. The rotation of the plane polarized light is referred to as a optical rotation. Compound having similar physical and chemical properties but differ in behavior towards plane polarized light are known as optical isomers, and the phenomenon is known as a optical isomerism. Next one, and the isomers that rotates the plane polarized light in the clockwise direction in set to the dextrorotatory, and it is here indicated plus sign. And on the other hand, the isomer that rotates the plane polarized light in anticlockwise direction, this is known as here levorotatory, and it is here indicated the minus sign. Next one, and the dextrorotatory compounds is here and the compound that rotates the plane of polarized light clockwise as it is approaches the observer to the right. Next, if the compound is here dextrorotatory, it is mirror image counterpart is here levorotatory. That is the rotates the plane of polarized light counter the clockwise to the left. It is here levorotatory. The dextrorotatory compounds have here positive specific rotation, while the levorotatory compounds have negative. Two enantiomers have equal and opposite specific rotations. For example of L-alanine and T-alanine. It is in the L-alanine is L-alanine. It is here plus dextrorotatory. It is also called as S-enantiomer. It is here levorotatory example. It is here T-alanine also called R enantiomers. Next one, diastereomers. What is a diastereomers? It is here sometimes called diastereoisomerism or in the type of a stereoisomer. Hence they occur when two or more stereoisomers of a compounds have different configurations at one or more but not all of the equivalent. It is a related stereo center and are not mirror images of each other. It is an example of the molecules 3 and 4 are not mirror images, so they cannot be enantiomers. And they are also not superimposable in space, no matter how much you rotate those in space. So they are not the same molecules either, and thus by definition they are diastereomers as they are non-superimposable but not mirror images of each other. The molecules 3 is 1s 2R, it is here 2-bromocyclobentanol, while it is diastereomer is 1s 2s 2-bromocyclobentanol. Next one, this type of trio and erythrio. It is here when two similar groups at non-identical chiral carbon are on the same side of the vertical line of the Fischer projection. The isomer is called erythroisomer. If the groups on opposite side, the isomer is called stereoisomerism. This here in the erythroisomerism is here same side of functional group, and stereoisomerism is called a opposite side of the functional group. Next one, what is the enantiomers? Enantiomer is the relationship between two isomerism. It is having and the isomers having molecules that are the mirror images of each other. Enantiomer have identical chemical and physical properties in non-achiral environment, but from the different products when related with the other chiral molecules and except the optical activity. A common example of a pair of enantiomer is dextrolactic acids and leucolactic acids. The lactic acids non-super impossibility of mirror images, it is a enantiomer. Next one is R isomer. An isomer is each of two or more common with the same formula but a different arrangement of atoms in the molecules. R configurations is the spatial arrangement of R isomer, and thus R isomer have it is a relative direction of the priority order in the clockwise direction. First, consider the atoms that directly bond to the chiral center. When the atomic number of higher, the priority of it is also get the higher. Next one, therefore it is here the substituent contains an atom with the higher atomic number bonded directly to the chiral center. That is the substituent gets the higher priority than the others. If two substituents have directly bonded atoms with the equal atomic number, then consider the atomic number of the next atom in those substituents. We have to check the atoms of the substituents one by one until the point of difference comes. Next one, S isomers. S configuration is the spatial arrangement of S isomer. S isomer has a different arrangement unlike that of the R isomer of the same molecules. The letter S comes from the Latin word, it means left-handed. Unlike R configuration, and the S configurations has the anti-clockwise direction of the substituent, that is from the higher priority of the lowest priority. Next one, the properties of enantiomers. The enantiomers have identical physical properties like melting point, boiling point, density, refractive indexes, etc. However, they differ in the optical rotations. One of the enantiomer rotates the plane polaris light to the right. It is example of say a dextrorotatory, and the other to the left it is a levorotatory. And the enantiomer have identical properties except in the presence of chiral reagents and solvent, while their rate of reaction are different. And the enantiomer have different biological properties. For example, L plus ascorbic acid is also vitamin C. It is more efficient than T minus ascorbic acid. And then minus nicotine is more poisonous than positive, I mean plus nicotine. Plus histidine is sweet, but minus histidine is tasteless. In some drugs which exits as a mixture of two enantiomers, only one enantiomer is active. A typical case that of anti-inflammatory agent ibuprofen, it is in this case only the S isomers ineffective, and the R isomers has no anti-inflammatory reactions. Next one is a conformational isomerism. It is a very important one, and the conformational isomerism is due to the molecule in space and arises to the rotation about the carbon-carbon sigma bond. It is also called a single bond. A larger number of isomers called conformational isomerisms are possible. And these are also called rotational isomers. The conformational isomerism cannot be separated. And the conformational isomerism, conformations of a cycloalkanes. First of all, first one is a cyclopropane. Cyclopropane is the cycloalkane with the molecular formula CH2 tries, and then it is a consisting of a 3-methylene group CH2 linked to each other to form a rings. And the conformational isomerism, since it is a plot molecules, in cyclopropane all the carbon atoms are in the one plane and the hydrogen atoms are situated below and above plane of the ring. In addition of the the angle strain due to the 60-degree bond angle of the does not permit effective overlap of sp3 orbitals. All the CH bonds of cyclopropan are eclipsed. Next on the cyclobutane. And the 4 carbon atoms in cyclobutane are not coplanar. Instant the ring typically adopts a folder or puckered conformation, and this implies that the carbon single bond carbon angle is less than 90 degree. One of the carbon atoms makes at 25 degree angles with the plane formed by the other 3 carbons. In this way, some of the eclipsing interactions are reduced, and the conformation is also known as a butterfly equivalent, and the bucketed conformation is a interconverted. Next is cyclobentane. The conformations of cyclobentanes are show the figure, and the planar conformations of cyclobentane, as in the case of planar conformation of cyclobentane, its 2 strain to the exits to the eclipsed CH bond. Both the half chair and the envelope conformations of a cyclobentane are the similar energy. Next one, cyclohexane. Cyclohexane is known as the exits in 2 main conformations. These are known as the chair and the boat conformations. Out of the 2 conformation, the most stable conformation of a cyclohexane rings is the chair conformations. It is a non-planar structure. In this, the carbon-carbon bond angle at 109.5 degree. So the chair conformation is free of strain. It is free of diagonal strain also. So it is and the chair conformation is a very stable conformation. Then next one is the optical activity. Optical activity is the ability of the chiral molecules to rotate the plane of plane polarized light measured using the polarimeter. A simple polarimeter consists of the light source, the polarizing lens, simple tube and analyzing lens. The specific rotation is the characteristic property of an optical active compounds. The literature specific rotation values of the authentic compounds can be used to confirm the identify of the unknown compounds. And for the example here, it is has been measured that the specific rotation of R2-methyl-1-butanol is a plus 5.75 degree. Even they can tell that the other enantiomer yes, it is as a 2-methyl-1-butanol must have the specific rotation of minus 5.75 degree without further measurement necessary. Next one is what is a chirality. A molecule of ion is called chiral if it cannot be superimposed on the its mirror images by any combination of rotations. Next one, the translations and some conformational changes. This geometric property is called chirality. It is a 2 enantiomers of a generic amino acids that the chiral. Chiral molecules are ion exits in 2 stereoisomers that are mirror images of each other called enantiomer, and they are often distinguished as either right-handed or left-handed by their absolute conformations or some of the criterion, and the 2 enantiomers have the same chemical properties except when reacting with other chiral compounds. They also have and some physical properties except that they are often have opposite optical activities. A homogeneous mixture of the 2 enantiomers in equal part is said to be a rash mix, and that is usually different chemically and physically from the pure enantiomers. Chiral molecules will usually have the stereogenic element from which chirality arises, and the most common type of stereogenic element is a stereogenic center or a stereo center. In case of organic compounds, stereo center must frequently take from of a carbon atom with the 4 distinct group attached to it in a tetrahedral geometry. A given stereocenter has the two possible conformations which give rise to stereoisomerism. It is a diastereomers and enantiomers in molecule with one of the more stereocenter. Next one, for a chiral molecules with one or more stereocenter, and the enantiomers corresponds to the stereoisomer in which the ever stereocenter has the opposite configuration. An organic compound with only one stereogenic carbon is always chiral. On the other hand, an organic compound with multiple stereogenic carbons is typically but not always chiral. In particular, if the stereocenter and it is configured in such a way that the molecules has the internal plane of symmetry, then the molecule is achiral and it is known as a meso compounds. Thank you.